Hello, everyone. Hope you're doing well. Today is a neat day. It is raining outside at the current time of recording. Hurricane Beryl is hitting Houston pretty hard right now. So our kind of thoughts and prayers go out to them as we keep learning a little bit about these normed vector spaces and as we start kind of pushing forward into what we can do with this new and added structure to our space. Now, what we saw last time is that a lot of the metrics that we've been learning about in the previous lectures, in the weeks of video lectures, have been induced by a particular norm. That we could have been using this sort of norm notation for many of the examples that we were working on. However, there's one particular example that we're unable to use a norm for, and that is that of the discrete metric. Recall the one where if you take 2 points x and y inside of a non-empty set x, and you say that this distance is equal to 0 if x is not equal to y, and 1 if x is equal to y. Sorry, got those flipped up. If x is equal to y, then the distance is 0, and 1 if x is not equal to y. There's a few reasons why this is happening and why this cannot be shown to be induced by a norm. And indeed, in your homework, you're going to kind of try and explain this a little bit. A few maybe suggestions about directions to be taking that. We have gone through and shown that the norm is continuous as a function that takes you from a norm vector space to the real numbers, that this is a continuous function. And if we're inducing the norm by this distance, right? If dx comma y is equal to the norm of x minus y, imagine what happens if you move a point y through a line that contains the point x. What if this was like x plus t times some sort of non-zero value z? If you pass y through this line, then take a look at what the values of this function d are going to be as you continue to allow t to vary. If t is equal to -1, then what you're doing is you're finding something like the norm of negative z, which is a non-zero value. And so because of that, this distance is going to be 0, or rather it's going to be 1 for this norm by the definition of how this distance works. It's the distance between something x and something that's not directly equal to x. If t is equal to -0.0001, then the same thing is true. The distance between x and x plus tz here, which is going to be just now it's going to be equal to the norm of -0.0001 times z, is still going to be equal to 1. The same thing is true if I approach from the other side. All of these values are going to be equal to 1 when I go through and plug in d of x and x plus tz into this metric and take a look at what this norm gives us. But something interesting is going to happen when I look at t equals 0. At this point, when t is equal to 0, I don't have this tz term at all. And what I'm doing inside of this norm is subtracting x minus x. That is the distance from x to x at this point. So when I have t is equal to 0, this is just the norm of 0, which is would have to be the norm of 0, which would then be equal to 0. This seems to break our notion of continuity. The function here of what happens when you plug in norms of things seems to be 1 whenever you have points that are not equal to each other. Then it jumps down to 0, and then it comes back up to being 1. Our only assumption from this, since we know that norms are continuous, is that you cannot have this sort of norm exist at all, but that gives you this sort of metric. So that's what is meant by the discrete metric is not induced by a metric. Now, there are more simple ways to go through and take a look at that, and you may be able to try and find some of those. See if you can kind of explore this idea a little bit in this particular homework problem. That's one particular reason. Another reason is this, to some extent, this lack of linearity. You may remember from taking a look at things inside of our linear algebra course, or 632, 689, whichever one you ended up taking, that we discussed something called a linear function, which we're also going to be discussing a little bit in our homework here. Recall that a linear function is a function f going from a vector space to some other sort of space. Typically, we've been seeing linear functions as going from a vector space to the real numbers, for example. Or we could even see it go from one vector space to another. So I'll do it in full generality here, such that if you have two vectors, v and w, inside of the vector space v, then the sum of those plugged into the function is the sum of their corresponding y values of each of the individual elements. F of v plus w equals f of v plus f of w. We also ask that when you plug in a real number for the inside of this function, then f of rv is equal to r times f of v for any real number here. So this is what is meant by a linear function. And one of the properties of a norm, that of homogeneity, seems to suggest that you at least have this secondary part. To some extent, it's some sort of homogeneity in the extent that if I want to be taking the norm of r times a vector, then what I can do is I can take the norm of the vector and multiply it times the absolute value of that scalar r that I'm multiplying the vector by. So I almost get this notion of scalar here, at least in the secondary component. And here I am replacing this first part here. If I take a look at what happens, that v plus w is actually less than or equal to v plus w. So I don't quite have it. This is a linear function. It does have some notions of a linear function with a couple of small changes here and there. This actually gets to be something called a sublinear function, which is kind of uses this less than or equal to sign there, although we won't be seeing many of those in this class. That is something that ends up being important later on in some analytical contexts. But because the norm satisfies property like this, you might be able to use this property to show that once again, that this cannot be induced by the discrete metric. So I encourage you to take a look at that. See if you can use the fact that if this distance, this discrete metric were to be induced by a norm, that is that the norm of x minus y was equal to the distance between those 2 points, try using the fact that any norm has to satisfy this equation here and show that there has to be a contradiction based on how the distance is defined. So what that means is that norm has to follow a very strict way of making a district work. A metric is a much more general context in which a norm has to have very much more constricted properties in order to be able to show that something ends up being a norm. So what we're doing is we're adding a lot more structure. And adding more structure means there's more things to be thinking about as we go through and solve these problems, which is why we start with metric spaces to begin with. We start with a level of generality that is pretty high. Although that means that sometimes it's difficult to be starting to think about pictures in these types of spaces. What it does mean is that in terms of our proofs and our theorems, we have to be thinking about less stuff. Say you're given a problem to solve in a homework, and you start working through it, and you're like, okay, well, how do I want to approach this? Do I want to approach this because this norm space that I'm working on is actually also a metric space and look at some of the metric space theorems? Or should I be looking at norm space stuff and look at lengths and angles between certain vectors? Or should I actually be looking at this as an inner product space, which is something we'll be talking about here in just a little bit, and start trying to apply some structure there? It becomes difficult to know the right way to pin down how to solve a problem. However, if you're given, okay, well, I know that this is a metric space, I need to be using metric space theorems, you can start tackling those a little bit more neatly, because you only know that those are the types of theorems that you need to be looking at. So now that we're in normed vector spaces, we get to kind of juggle a little bit. All of our normed vector spaces are also metric spaces, given this. Oops, did my pen stop working here? My pen may have stopped working. I'll take a look at that. So now that we have that a normed vector space can be given this metric structure to it as well, we now have to be thinking of normed vector spaces as having lots of different theorems that can be going on about it. In particular, any of the theorems, any of the properties, any of the definitions that we discussed from our metric spaces apply to normed vector spaces as well, because all of the norms have a metric that goes right along with it that acts very much in the same way. So as we discuss things like norm vector spaces, be thinking about some of the parallels that happen with metric spaces. How do you draw your pictures differently? Do they work very much the same way in the type of context that we're working on? As we go through this next topic of equivalent norms, how does this equate to the notion of what we talked about in metric spaces called equivalent metrics? Like, you may be able to take a look at what we have here for our definition of equivalent norms here in the indented region and realize that this looks a lot similar to how we might say metrics are equivalent as well. So even though multiple norms can be defined on a space, It is not the case that all norms have the same convergent and Cauchy sequences. Same way that you could be defining multiple different metrics on a space and they all just look and feel very different. But just as with equivalent metrics, we'll say that two norms are equivalent if, whenever you try and write these out, and we'll write them here. This is a typical type of notation that we will use to talk about two different norms. If we're not talking about something like the 1 norm, we talked about the L1 norm and the L2 norm last time. If we're not trying to talk about those in a particular context, then we'll just number our norms if there are two of them on a space. So a vector space V might be given a norm V1 or norm 1, as well as a norm V2. The difference in the notation of these is that we are looking at the same elements on the space, but we are considering the norm on that space to be something different, right? So for example, convergence in this space might look different than convergence on this space. Remember, convergence is a notion of closeness. Well, if I just take a look at the two sets themselves, they are 100% identical. Elements themselves inside of these sets are all exactly the same. We don't know what elements are close to each other until we institute a norm, and these two norms could have very different notions of closeness. But we can define norms in ways that are very similar to each other. Take our 1 norm, for example, that we talked about last time, which was taking the integral of a region of the absolute value of a function dx. Here we would be on something like the continuous functions going from a to b. If we take this norm here, then the way that another way we could define this norm, and we'll call this one a times 1, is to take it and just take it and divide it by the value of pi, for example. 1 over pi times the integral from a to b of the absolute value of f times dx. But closeness inside of these two norms is very much the same. Anytime that I measure a norm of an element here, it's going to be the same as measuring a norm of something inside of here. It's just that I'm going to be taking that distance and dividing it by pi. So the numerical value that I attribute to a function value or a function inside of this vector space is going to be different. But in terms of what ends up being close to each other or convergence, it's not that big of a deal. If we know that, for example, you have a sequence of functions that converges to 0 inside of the function f sub n minus f, if those things go towards 0 inside of that norm, then we can also say that they will converge to 0 with respect to this altered 1 that we are working with here, because all you're doing is taking the definition of the norm of 1 and dividing it by pi. The same thing is true if you go the opposite direction. This is an if and only if. If I take something like 1 over pi times this integral and say that that converges to 0, well, the 1 over pi is not converging to 0, so the integral must be converging to 0 in that respect. To kind of clarify that, we say that any two norms are equivalent whenever there is some sort of constant such that the norm of one element is bounded above and below by the norms of the second element, either multiplied by m, and then the norm of 1 is less than or equal to m times that norm of x sub 2, and then also bounded below by 1 over m times the norm of that x sub 2. So we've talked about what two equivalent metrics look like. Let's take a look at two norms that are not going to be equivalent. So we've defined a couple of norms in little L1 space. So those here are going to be the norm of x sub 1 is going to be taking a sequence x sub I going from 1 to infinity here, summing the absolute values of each of the elements inside of that sequence gives us something called the L1 norm. We also have the little L infinity norm. This is something else that we have seen. We know that the metric that this induces is that of the uniform metric, the one in which it's very difficult to kind of go through and make some sort of convergence here because you have to basically have your sequences converge uniformly. And you can see that the way that that works here is you take the norm x sub infinity and you get the supremum of the absolute values of these x sub I. It turns out that these norms are not equivalent on the space little L1. That is, that we can take these two norms, define them on the same space. The little L1, remember, is going to be the space of all sequences x inside of a big space, which is these are just sequences of real numbers, such that the sum of the absolute value of x sub I, we're going from 1 to infinity, that this sum is less than infinity. And anything that exists inside of this space could also be given the little L infinity norm. Why is this? Because I know that I can define a finite metric on this space. As long as my sum of these x sub i's is finite, then I know, in fact, the supremum over all elements inside of this series has to also be finite, that it cannot go off toward infinity. So I can define these two norms on this space and show, in fact, that these two things are not equivalent. And let's see how we could go through and do that with these two problems like here. Let's let a vector space V have two equivalent norms, norm 1 and norm 2. Let's show that any convergent sequence in V1, norm 1, converges in V, norm 2, and vice versa. Very similar to the examples that we saw over on the right-hand side of the previous slide. So how are we going to show that these two have the same convergent sequences? Well, what we'll do is we'll say, let's say that we have a sequence S sub n converge to S in the space of V norm 1. Then we want to basically end up with the statement. We want to show that this same sequence converges to S in V norm 2. We'll be practicing this notion in our homework a little bit as we start switching out the notion of convergent sequence with something else. So in fact, this part here is going to be one of our homework parts. But I'll go through and walk through it a little bit so that you can start seeing what kind of goes on as we try and work through this problem. So this is our goal. We want to say that we have a convergent sequence here, that in fact, that convergent sequence is the same in norm sub 2. So how are we going to go through and show that? Well, we need to be using the fact that the norm of any element inside of here, and that includes the norm of S sub n minus S in terms of the 1 norm, is going to be bounded above and below by norms in terms of S2. And then same thing over here in terms of S sub n minus S sub 2. Now we get to use this fact. We can also flip them. We can even say that S sub n minus S sub 2 is less than or equal to m times S sub n minus S sub 1, or then greater than or equal to 1 over m S sub n minus S sub 1. So because the norm 1 and norm 2 are equivalent, and this implies that there exists values of m, and technically these values of m could be different based on which type of the definition that I'm using, but there exists m1 and m2 in the real numbers such that I have this boundedness between these two. And it's something that you might try to go through and do is see, okay, well, what inequality is going to be useful for me here? I recommend the inequality here, hint, I recommend the inequality that the norm of S sub n minus S sub 2 is less than or equal to the norm of m, or m1 times S sub n minus S sub 1. I recommend trying to use this particular inequality to show that, in fact, if you have a convergence here in the norm 1, that in fact you have a convergence here in terms of norm 2. Remember that you also want to be able to do the vice versa. Let S sub n converge to S in V norm 2. We want to show that S sub n converges to S in V norm 1. Now, many of you are going to be able to see how this works. And once you get to that point, you can see that in many instances where this is happening, the proof is going to be very similar. When you try and say that a sequence converges in norm 1, then it actually converges in norm 2. The flip side is what's going to happen to be able to show the vice versa side of this. So you are okay once you see that happening to say that the proof is similar, going from one side to the other and then switching the order of those two things. So now that we know that these two equivalent norms have the same convergent sequences, we'll be able to show that these two things are not equivalent norms if we can find a sequence that converges in the 1 norm, but does not converge in little l1. In particular, we're looking at the space of things that converge in little l1, which we recall means that we are looking at the norm of x sub n minus x. I guess we're talking about sequence here, so I'll use S sub n minus S in the infinity. We recall that that's going to be the supremum over all. Let's see, what kind of notation could we use? Let's use k in the natural numbers of the values of S sub n k minus S sub k. So this here, what I mean for S of nk is that I'm looking at a sequence of S that's called S of n, and then the elements of that sequence will be S of nk as k goes from 1 to infinity. So that's how I'll fix my notation here. And I'll do the same thing with the sequence S, which will be the sequence of S of k, where k goes from 1 to infinity. So to define a norm, an infinity norm for S of n minus S, then what I'm doing is I am taking the supremum over first, fix an entry between the two sequences, take their difference, and then take a supremum over all the possible differences between the two sequences. For example, we had something in our midterm exam that talked about something converging inside of this D infinity metric, which was we start with 1, 0, 0, then we go 1, 1, 0, 0. Basically, the idea is that you're continuing to add a 1 every time that you add a element into this, or go one sequence farther inside of this sequence. And indeed, this ends up not converging in little L infinity, as we saw there. And the reason for that is that this norm here does not end up getting to go down towards 0 at any point. Could it converge to the sequence of all ones like it seems like it's doing? Could it converge to this spot? The answer is no, it cannot, because the distance between, if I were to call this S and I were to call this S of 2, S of 1, and S of 3, then this norm difference here would be the S of n minus S would be greater than or equal to the difference between, at one particular element, the difference between 0 and 1 for that element. Here, it would be 0 and this 1 right over here. These guys would have a difference of 1 in between them, so the distance between S3 and the element I'm calling S would be 1. But the same thing could be said for any further sequence as well, S of 4, S of 5, S of 6, because there's always going to be a 0 inside of that sequence, and this sequence would be full of 1s. In fact, this could not converge to the point S. We could even clarify that a bit more now that we've talked about Cauchy sequences, to say that this sequence here, in fact, is not Cauchy. The distance between any two sequences inside of this set would be, of this sequence, would be 1, because there's always going to be a difference between 0 and 1 in some adjacent sequences. Because of that, the sequence cannot be Cauchy, and we know that any convergent sequence must be Cauchy. So if the sequence is not Cauchy, then it cannot converge. Just kind of giving a general notion of what that looks like here, just as a reminder from our going through and talking about that in our midterm exam. But let's go through and actually now find a sequence that converges in little L infinity, but does not converge in little L1. So let's see if we can find out what that might look like. Here's one that we could try. Let's take S of 1 to be equal to the sequence of 1, and then 0, and 0, and so on and so forth, kind of like the same start as the one that we just gave as our previous example. What about S of 2? What I'm going to do for this one, because remember last time what happened was we keep adding 1s, and so the distance between any two sequences ends up being very small or very large from each other. So here's how I'm going to change that. I'm going to make it, instead of 1, 1, 0, I'm going to make it 1/2, 1/2, 0, 0. So each of the elements inside of the sequence are also, the non-zero ones are going to be divided by 2 as I go through and do this. S of 3, I'm going to make it so that the first 3 elements, which were 1s in our previous example, are now 1/3. So how am I defining the sequence S of n? I'm making it 1 over n, 1 over n, dot, 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 1 over n for n elements of the sequence, and then I am making it 0 beyond that point. Here is a sequence of elements that I'm going to claim converges to 0 in this little L infinity metric. Remember that we say that something converges in the little L infinity metric if it converges uniformly. This sequence is indeed going to converge uniformly here, and we can see that here because the largest possible distance between any given element and the sequence of all zeros, S equals just 0, 0, 0, 0, that's the largest possible distance between these two elements in L infinity, oops, there we go, is going to be supremum over all n in the natural numbers of the sequence of S of n comma k minus S of n. And then that is going to be less than or equal to the largest possible distance between them, which will always be that of 1 over n and 0, which could happen here just at the very first term. Past that point, the largest distance that they could have is either going to be 1 over n, or they're going to be 0 at the very end there. So that's actually not going to be okay as well. So in this little L infinity distance, then the distance between S sub n and S here is going to be equal to 1 over n, and that's a sequence that goes towards 0. So this sequence ends up converging in little L infinity because with respect to that metric, these things continue to get smaller and smaller in their distance from each other. But I claim that they do not converge in little L1. Remember what it means for something to converge in that space. I'll call that one D1 here. To take S sub n and S, we would take, in little L1, we would use the metric that we were given for that one from the last time. So recall what that one was. We did little big L1 up here before. So let's recall what's the norm in 1 is going to be. That's going to be taking the sum of x sub I, as I goes from 1 to infinity, of a sequence Sx of taking this sequence here, x sub n. So if we're taking the distance from S sub n to S, then what we're doing is we are summing I equals 1 to infinity of, what is this? This is going to be S sub n comma k, should be k here, minus S sub k. So it should be this distance here. And so that helps us measure the distance between these sequence elements. But what is this going to look like? Well, S sub k, this sequence here is always 0. So I could just plug in 0 for that part. And this sequence is oftentimes 0. We only know it's non-zero whenever you're looking at an index going from 1 to n. So I can ignore the rest of the terms. And then the rest of the terms is going to be equal to 1 over n. Sum goes from k goes from 1 to n. This sum here is going to be 1 over n. And in fact, this sum is going to be equal to 1 for all values of this S sub n that I could be working on. So this is true for all n. So what does that mean? That means that the distance from S sub n to S can never be underneath epsilon because, in fact, they are always going to be 1 away from this sequence of S. Now, taking a picture and trying to imagine what this looks like, you could think of in terms of functions that one of these functions needs to, like in L infinity, this is saying that you need to take these sequences and have them converge uniformly. And this other one is trying to have them converge in series, converge in the whole series of the sequence that you're working with. Think of the series here as like a discrete version of the integral. It's kind of like having a sequence of functions converging to f in big L1 or inside of an integral. So these two notions of convergence end up not being equivalent to each other. They don't work exactly the same way. They don't have the same convergent sequences. And so because of that, we can say that these two are not equivalent norms. In our homework, we're going to be working more with norms that are equivalent and see kind of how that proceeds from there. But I go through and talk about that a little bit because norm vector spaces have a particular way how they'd like to be shown as complete. Norm vector spaces, like metric spaces, have certain properties that only show themselves whenever we understand that they are complete spaces. For example, we know that Cauchy sequences converge whenever we're in a complete metric space, and we get the same sort of thing in a norm vector space because we know norm vector spaces are metric spaces. What that does is it sometimes allows us to say, okay, well, I can take a sequence of things that I know are close to each other and actually get that these things converge because of the completeness of the space. What it does is it kind of just saves the analyst a headache. It says, okay, I don't want to have to deal with showing that what this converges to. I just need to be able to show that this sequence is Cauchy, that the elements are close to each other, because that works a lot more easily for me. We've seen some examples of how this could work in the past. We've also seen this notion of like diameters of a set being able to close and having points of a sequence inside of concatenated elements of sets continuing to grow smaller. And having a property like that in a complete space allows us to get convergence of a sequence. Complete spaces allow us to also sometimes consider, do we have some things like an intermediate value theorem inside of here, which is something that we can only say is true inside of a complete space. We need completeness for some of those types of properties. So completeness of a norm vector space It's going to come from these series that we've been working on. That's why I introduced series back in the previous example, is that the easier way to be able to define completeness for a norm vector space is in terms of series. And you'll see that in the notes section of my video lectures, I've gone through and given a quick PowerPoint presentation of just some quick review of series in case it's been a while since you've seen some of those concepts. One of those concepts is going to be that of converging absolutely for a series. And you'll go through and see what that is. And once you've seen that, you'll kind of make a little connection here about how we define converging absolutely and what is to come after this. But because norms define a metric in our space, we can still get this notion of Cauchy sequences. And so we can get the same sorts of properties as what we were looking at. It's a bit easier to think of completeness in norm vector spaces in terms of infinite sums. Let's say that you have a Cauchy sequence U sub k inside of a norm space V. Recall that something to be inside of this, what we're saying is that there's going to be, for all epsilon greater than 0, there exists a capital N in the natural numbers, such that whenever you have some little n and little m bigger than that n, then that's going to imply that S sub n minus S sub m is going to be less than epsilon. So that's what we mean for this Cauchy sequence here. Well, if we take that notion and redefine it in a little bit of a different way, let's say that that Cauchy sequence, I'm actually using the letter U here, so allow me to go back and change this to UN and UM respectively. Then I could redefine a new sequence based off of differences inside of this space. Let's define another sequence. Then we'll call it S of k. Let's make S of 1 equal to U sub 1. S of 2 equal to U sub 2 minus U sub 1. S of 3 will be U sub 3 minus U sub 2. And if we continue going, S sub n is going to be U sub n minus U sub n minus 1. Well, how do I understand this sequence? Notice that this is a difference sequence. It's saying, okay, you first take S1 to be U1, and you take S2 to be the difference between the two elements between U1 and U2. Well, what happens if I now add elements of S of k together? If k goes from 1 to n, then what I'm doing is I am taking the sum as k goes from 1 to n of U sub k minus U sub k minus 1. In particular, I'm doing this all the way down to the bottom term, which is then just going to be U sub 1. So I'm just going to be having that outside of this little series here. And if I look at this and what this forms, this becomes a telescoping sum. U1 plus U2 minus U1 plus U3 minus U2 plus dot, 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 plus U sub n minus U sub n minus 1. And that telescoping sum is just going to give us U sub n. So this sum, as k goes from 1 to n of this series, is U sub n. So if this series U sub k converges, what that means, what we're saying is that the sum of these S sub I has a limit in the infinite series. Typo here should be the sum of the S sub I here has a limit in the infinite series. Now, if that's going to have a limit in the infinite series, then in fact, the S of k also have to converge. They have to converge to 0. We know this about series is that if they converge, the series converges, then the individual elements of that series must converge to 0. Okay? So let's talk a little bit about some of these series that are going to be useful for us. Well, why do series come into play at all? Well, it's because that vector spaces have vector spaces. Vector spaces have bases. And recall that a basis is something we were talking about in the previous video lecture, which tells us that there is a way to write any vector uniquely as a linear combination of a collection of vectors. Now, there's actually two forms of bases. One basis that we talked about before was called a Hamel basis. A Hamel basis, remember, is one that says that you can always write something that is a finite sum of I equals 1 to n of elements inside of a vector space, as if this is equal to 0, then in fact, that this meant that the alpha sub I was equal to 0 for all I inside of the set from 1 to n. Right, this was the notion of linear combination that we have used a good bit so far in linear algebra, as well as in defining things with bases there. But there's something that we typically brush over in a linear algebra class. which is that in those types of classes, we're working with matrices. Matrices work very well over finite dimensional vector spaces. But we've already just seen several different examples of vector spaces that are actually infinite dimensional. Now, let's take a look at little o1, for example, the one that we were just looking at. This is, recall, the sequence of all elements that where if you take the sum of the absolute values of them, that the sum is finite for this. This has a infinite dimensional basis. I'll show you what this is. You take the sequence of 1, 0, 0, dot, dot, dot. Then you take 0, 1, 0, dot, dot, dot. You take 0, 0, 1, 0, dot, dot, dot. You can kind of see what's happening here. I'm continuing to put a 1 inside of every element of every entry that you could have it in a sequence, and then putting zeros elsewhere. Now, this notion of little o1 and this basis that I'm forming is infinite dimensional because I can't stop at any one spot and say, okay, well, any element inside of little o1 could be spanned by just taking and putting ones inside of the first n positions. How do we think of this in terms of Rn? In Rn, we have a similar notion. In Rn, we will take our finite coordinates this time and just put a 1 inside of each coordinate that you could be putting, you could be using inside of the basis for Rn. But here you get to stop at some point because you only have finitely many coordinates. So you can just say, okay, there's going to be n elements inside of a basis for Rn. In little L1, we cannot do that. There are infinitely many coordinates, which we now call entries of a sequence, inside of little L1. And so this is an infinite dimensional system. There are other spaces that are also infinite dimensional. The space of all polynomials is also going to be infinite dimensional. You can think of taking the entries, the coefficients of a polynomial, and continuing to string them all along. And because you could have a polynomial of however big a degree you would like, that coordinate is infinite dimensional. So is the collection of all power series. That's going to be an infinite dimensional space as well. But those two spaces in particular end up having different types of bases. We have to separate the two types of bases here because now we are in a world of infinite dimensional vector spaces. Whenever you're on an infinite dimensional space, sometimes you have a Hamel basis, which is whenever you have a sum of, when you're looking at particularly the definition of linear combinations, or linear independence here, that whenever you're taking and finding that for your particular basis you're choosing, that you have a finite sum as I goes from 1 to n of alpha I, e sub I is equal to 0, then in fact, each of the elements themselves have to be 0. That works very well inside of a space of polynomials, because we know the space of polynomials has a basis of 1, x squared, x cubed, so on and so forth, all the way up to however big a degree that you would like. However, polynomials stop somewhere. So at some point, if you're given a polynomial, p of x, then you know that this is a sub 0 plus, and I'll just go ahead and put in some numbers here, 3 plus 2x plus 0x squared plus negative x cubed plus dot, dot, dot. And eventually, I'm going to get to, say, x equals 1993, something like this. So x is 1993 times a value of 97. So here is that polynomial or something like this. This is a polynomial that itself is going to be a sum of finitely many terms. And so if I know that, in fact, each of the coefficients of this are going to be 0, I will take a look at x goes to I, as I goes from 0 to 1993, then in fact, if I know that this is equal to 0 for any given collection of a sub I here, then in fact, I know that the a sub I all have to be 0, that this is actually the 0 polynomial. If I know that this polynomial is the 0 polynomial, then that means each of the coefficients have to be 0. This is a notion of a Hamel basis, which works well for the space of polynomials. But this doesn't work well for something else. Let's consider the space of all power series. If we look at the space of all power series here, remember that a power series is you can be taking something like x to the I, and you can give it a sequence based off of that. So we could go, for example, to the sum of 1 over I squared times x to the I. And we could take that sum to go from I goes from 1 to infinity. This is an example of a power series where now we have infinitely many terms inside of this. Now notice that any finite collection that I might take here, for say I goes from 1 to n of these alpha sub I, x sub i's, if I take this series and say that this is equal to 0, well then past that value of n, whatever that finite bound is, I still have non-zero elements here. So I actually am not able to conclude that in this case that alpha sub I is equal to 0 for all I. That's not what I get to conclude in this space. I would have to go through and extend this to be infinite in the number of terms that I'm allowing here inside of this sum. And that's exactly the notion of a Schauder basis. A Schauder basis says that if you have a sequence of elements inside of a norm vector space, then we would say that you get a Schauder basis for it if for any vector inside of the vector space, there is a unique sequence. And notice the sequence is now of an infinite collection of numbers, alpha sub k, such that the value of x is equal to this infinite sum, alpha sub k times e sub k. Infinite sums like this exist naturally in infinite dimensional vector spaces, like the space of power series that we were just looking at from before. So power series have infinite dimensional vector spaces that require Schauder bases. And that's because you could look at each of these collections of these x to the power of I, and any element inside of there cannot be just written as a finite sum of these constants times x of I. They always have to be infinite sums. So that gives us the notion of a Schauder basis. That's basically the difference between Hamel basis and Schauder basis. Hamel basis means every element in V is a finite linear combination of its basis elements. Whereas a Schauder basis says there exist elements in V that are infinite linear combinations. So a Schauder basis would mean there are elements, I'll have to erase that infinity here. There are elements in V that are infinite linear combinations. And I'm going to put this last part in quotes because the definition of linear combination that we get from looking at this in linear algebra is the same definition of linear combination. I'm using infinite linear combinations as more of a way of evoking something in us to say what this is. But at this point, we just call it an infinite sum. It's an infinite sum whose basis elements are the kind of constituent points. It's scalars times basis elements. Linear combinations are typically said to be finite sums, whereas infinite linear combinations are things of this form. So this is how we would write that. It's just an infinite sum is how we would write it. So here is that example that we were just spelling out. The polynomials form a Hamel basis for the set of all polynomials over the real numbers, and they form a Schauder basis for the set of all, and to be clear, these are convergent power series that eventually give you a function on whatever space that you're looking at. So let's talk a little bit about what happens with these differences between these types of bases. So it turns out that all norm spaces with countable Schauder bases are separable. Kind of going back to what we were doing last week. Remember we said that we like separable spaces because it gives us a ability to control the size of it in terms of distance. Separable, importantly, means that there exists a countable dense subset inside of that space. We actually did something with this a little bit with talking about how polynomials, the space of polynomials is separable. We can actually say the same thing about the space of power series because they are going to have a countable Schauder basis. And that Schauder basis is going to look like this. The Schauder basis for the space of convergent power series is the same basis, 1x, x squared, x cubed. And because this is countable, this theorem applies for this. And the way that we do this is we take this following set, which is, notice a few things about it. One is that you're going to be taking your scalars in the rational numbers, kind of like how we did in that homework problem. We're going to be multiplying those times the elements of the Schauder bases, and we're only going to be considering linear combinations, or for emphasis, finite linear combinations with respect to elements inside of that Schauder basis. That turns out to be a countable set. This space is countable. So what's going on here? This is a Schauder basis. So John, why isn't this the sum as k goes from 1 to infinity? If I allowed this to be the sum as k goes from 1 to infinity for this, I do lose countability of this set, because now I'm looking at sequences of rational numbers here, which we know is uncountable, just like sequences of integers would be uncountable. So I'm not allowed to do that. What I need to be doing instead is looking at any of those sequences that are, get this, eventually 0. So these are the sequences of alpha sub k are eventually 0. And so what that does is it says, okay, well, now you're taking a look at the alpha sub k that are eventually 0. As k goes from 1 to infinity, so that you can ignore any of the parts of the sequence that are past some value of capital N. So the sequence alpha sub k is going to be eventually 0, which means now we get to retain our notion of looking at this space. Now, let's talk a little bit about this. These are finite sums, so now we have another issue, which is how are we going to show that we are able to approach infinite sums with finite sums? And I have good news for you. Every infinite sum can be approached by a finite sum. What does it mean to take the sum as k goes from 1 to infinity of alpha sub k times e sub k? Well, what that means is, to put infinity here as the sum is to say that this is a limit of its finite sums. That this is the limit as n goes to infinity of k goes from 1 to n of alpha sub k, e sub k. And recall that, again, we can show density by saying that for any element inside of this vector space V, there exists something inside of this set that we're defining that converges to it. And that's exactly what we get right here. So finite sums end up being enough not to cover the entire space, but to be dense inside of that space. So that gives us the notion behind this theorem, that all norm spaces with countable Schauder bases are indeed separable. That can also be used, this theorem ends up being pretty tight here, because it turns out that spaces like little L infinity, which do not have countable Schauder bases, are not separable. There are uncountably many sequences consisting just of the digits from 0 to 9, and each has a distance greater than or equal to 1 from each other sequence of that type. So little L infinity is going to end up actually not having a Schauder basis at all. So that's interesting as well, is that some spaces, that even those that are infinite dimensional, may not even have Schauder bases to work with. And that's something to kind of keep in mind as we go through this, is that the Schauder bases are worked very neatly whenever we want things to converge inside of a space. Some spaces not very neat and work neatly with the sort of Schauder basis, but every vector space does have a basis. This is something that's just a little bit of an Easter egg here with this. It's not something that we are going to need, but this is a theorem that comes to us from abstract algebra, which says that every vector space has a Hamel basis, in parentheses, because whenever we refer to basis without clarifying, we will mean a Hamel basis. So every vector space does have a Hamel basis, although it's possible that many of them don't have this neat little convergence of things that a Schauder basis can provide in terms of infinite sums. Little L infinity just has this notion of not having this neat way of having things converge using a sort of Schauder basis. And you can think about why that might be if you considered looking at the Schauder basis of like sequences that we've been talking about from before, where ones exist at some spot. Then any finite sum of those sequences is not going to converge to a little L infinity sequence that is non-zero in every single element. In fact, those that are all constantly 1, for example. So you can kind of try and piece that together a little bit, which is that this Schauder basis idea does not work very neatly for some spaces in which convergence is very, very tricky. C0, on the other hand, is a subset of those sequences. We recall that C0 is the set of all sequences that these converge to zero. This does have a Schauder basis because convergence is very nice inside of here. The types of sequences that we were looking at before are not inside of C0, but sequences like 1, 1/2, 1/3, 1/4, all the way to 1 over n, continuing on from that, that is an element inside of C0. So taking a look at a Schauder basis, which is this one right here, it's going to be the set of putting 1 in the nth coordinate and then zeros elsewhere, that this works neatly as a Schauder basis for this space. Quick typo here that I need to mention is that C0 is for infinite sequences, so this actually is not going to exist. This is going to go off toward infinity. My bad. So I was looking at this as like a finite sequence, should be for an infinite sequence. We say that any complete normed space is a Banach space. Banach space means that you have a normed vector space that is also with the notion of completeness. Now, Banach spaces are one of the objects that are studied in and of themselves because Banach spaces actually create a world of mathematics, which is called operator theory. And we'll be seeing some of these operators here in the upcoming week, which is operator theory is talking about functions that are linear going from one complete space to another. This is the birth of an entire world of mathematics that had its origin at around the time of John von Neumann, which would have been about 100 years ago, when he was studying some quantum realities. It turns out that operator theory is a great way to start generating field theories. And has very neat applications in the world of physics. That's where a lot of this stuff started trying to come in. And we see a lot more operator theory go into more theoretical side in the kind of mathematics that I grew up in. One of my particular research interests is operator theory. I work with these types of operators that go from one Banach space to another, or maybe Banach spaces with other different types of structure. So the thing is that now that we are in this world of complete normed spaces, we have a good bit of structure to go with us. We know normed spaces are measure spaces. We know that they also have a norm on them, so it's able to take lengths. We're able to take angles if we want to. We can also have these be complete spaces, and a Cauchy sequence is going to converge. So we're going to be able to talk about norm spaces a good bit this week and next week. And unfortunately, we don't have time to talk about all the wonderful things that I would love to get the chance to share with you. But this does get us started here with talking about these Banach spaces. Let's end with one last theorem, which is how we can characterize completeness, once again, in terms of infinite series. Let's first borrow a definition from infinite series in calculus. You maybe know this from either looking at the review slides or from your own Calculus 2 class or having taught this class, which is that we would say that a series sum of a sub k in calculus, I'll use a instead of alpha, of a sub k converges absolutely if it converges with absolute values around it. And we know that this has some very neat properties around it. Things that converge absolutely kind of work very neatly with some of our power series theorems. In particular, they works well with this interval of convergence. And basically actually helps us prove things with that interval of convergence. A little bit more on that in the optional video that I posted in section 6-3. So kind of getting in that direction there. And they also are just some of the nicest series to go through and converge. There's the sort of types of series that you can look at it and say, okay, that this converges. It's not necessarily the case if you have something like -1 to the k times 1 over k here. Those types of series, it's a little bit trickier to go through and converge. You would at least need something else, another test, to make that work. This one ends up to converge because of the alternating series test. But we will use that notion here to say that an infinite series in a normed space converges absolutely if the sum of their norms is less than infinity. Notice that this lines up directly with this theorem here for calculus, because in terms of the real numbers, the norm of a number is the absolute value of that number. Those things line up. Going back to like video lecture for 8-0, those two things are meant to line up with each other, our notion of norm and our notion of magnitude of a number, A. So this is the exact same definition here. So we're just borrowing it verbatim. It turns out that a norm vector space is complete if and only if every absolutely convergent series converges. What are we doing here? Do you notice something that looks different about this word of complete and what's coming after it? Typically, when we say something is complete, we would say every Cauchy sequence converges. And we are changing that to say every absolutely convergent series converges. So what's the difference here? How are we going to make the connection? Do you remember us going back and before we talked about bases for a little bit? Do you remember us talking about how given a Cauchy sequence that you could be turning these things into infinite series where those series converge towards zero? We could do this sort of operation. Well, that's actually the main idea behind this proof, is that you can take a Cauchy sequence and turn it into an infinite series by looking at the differences between elements of a Cauchy sequence. And if we know that we're in a complete set, then in fact, absolute convergent series should converge because that the Cauchy sequence, the distances are going to go towards zero and the sum should exist. Then the opposite is also going to need to be true because absolutely convergent series, we should be able to form a Cauchy sequence out of the partial sums of that absolutely convergent series. But we'll go through and make sure that we've got all of the general notions of that. A lot of this proof is going to use the notion of series to kind of make sure it makes sense. We've already identified the notion of Cauchy sequence and what I'll be calling Cauchy sums above. So we will use that Cauchy sequences converge if and only if Cauchy sums converge. So to be clear about what I mean by that, I'm looking at the sequence of S sub n. If this is a Cauchy sequence, I believe actually I used U sub n up there for that lettering. Then in fact, we will say that the sum of the S sub n, where S sub n is equal to U sub n minus U sub n minus 1 whenever n is greater than or equal to 2, or where S sub 1 is equal to U sub 1, that this sum is what I will call a Cauchy sum in what is to come. So let's go through and prove both directions here. Starting with the vector space V being complete, we want to show that this series converges, or this absolutely convergent series actually converges. Now, another thing to kind of mention here is that it seems like we're saying an absolutely convergent series, and we're already saying that it converges, right? I think back to people who would say, okay, well, John, you have put convergent in the name of the series, so what do you mean it converges? It is very possible that this series does not converge. And one thing that you could do for that is you could say, okay, well, I'm going to take myself in the form of the rational numbers, and I'm going to take my sum to be that of taking elements like of the form 1 plus 0.4 plus 0.01 plus 0.004. I use this type of example quite a bit, but you could see that these are all rational numbers when I consider their partial sums. And in fact, the sum of these elements is going to be less than infinity, even when I take their absolute value, because they're all positive, but that these do not converge to anything in the rational numbers because where these are going off toward is the square root of 2. That's the exact notion of completion, right? So absolutely convergent series, by our definition, does not need to be a finite value. It does not need to be as something that exists inside of our space. So that's what it means to say we want to show this absolutely convergent sequence of series converges. Well, first, what we call the tail end of this sequence, which is something that perhaps you saw in an undergraduate analysis course, or sometimes it's even talked about in Calc 2. The tail ends of these sequences, of the norms of these sums, actually go to 0 because the sum of the norms ends up converging. That's a little bit of a starred proof. I included that in the very last slide if you want to see where that proof comes from. Hence, what the goal is to show that the finite sums, so goal is show finite sums, the partial sums of this form a Cauchy sequence. We want to show that these finite sums form a Cauchy sequence because we're starting with V being complete, and we want to show that absolutely convergent series converge. So we start with a series that converges absolutely, and if we can show that the finite sums form a Cauchy sequence, well, where the finite sums converge is exactly where this Cauchy sequence is going to converge. And if all Cauchy sequences converge, then the finite sums must also converge to that very same point. And that's exactly what we end up showing right here, which is to say that anytime that you are given finite sums, then that ends up being the sum as, because these are, you can look at these two sums as like canceling out terms, this one going from 1 to n, this one going from 1 to m. Then the difference, the sum as n goes from n plus 1 to m of a sub k is what we're left with. Here I'm kind of making an assumption that m is bigger than n, but without loss of generality, we could also switch the order here and have this be from m plus 1 to n as well. So this is an assumption that I'm making at this point. But I could always add more terms to that series and then also do a little bit of a triangle inequality at this point to recall that if you have a sum of terms and you're taking its norm, then you can make that the sum of the individual norms by using the triangle inequality. Again, that is exactly what we would do in terms of two elements. We're just doing that here with respect to a bunch of different elements here. And so now using that triangle inequality, we know that this sum by our star term goes towards 0. So the series ends up being Cauchy by definition of the fact that we're looking at something in the mth partial sum and the nth partial sum past a certain point being less than or equal to, or heading up towards 0. So this series has to converge. Then going the other direction, we're going to now say that absolutely convergent sequences converge and turn x sub k from a Cauchy sequence into something that ends up converging. So let's see if we can do that. Without loss of generality, we're going to be able to find elements of this series, x sub n minus x sub m, to be less than or equal to 1 over 2 to the I. I'm going to choose that in particular. These n sub i's are choices of what my cutoff points could be, so that past that cutoff point, elements inside of that sequence are close enough to each other to be within 1 over 2 to the I of each other. And I can do that for any value of I, because this 1 over 2 to the I is my epsilon, and I know that by the definition of Cauchy, for all epsilon, I can get this statement. So that's what I'll do. So I'll pick the n sub I so that the sequence n sub I is increasing, just to make sure that I'm actually going to get a subsequence, what I choose here. So that in particular, that the norm of x sub n sub I plus 1 minus x sub n sub I is less than 1 over 2 to the I. I can always do this because as long as n sub n and m are bigger than n sub I, then that's going to be the case. And I'm choosing n sub I plus 1 to be bigger than n sub I to make that work. Then what do I get from that? The sum of each of these norms is going to be less than the sum of this 1 over 2 to the I, and that's going to be equal to 1. This is now an absolutely convergent series. So what have I just done? I have taken a subsequence of this Cauchy sequence and showed that it was an absolutely convergent series. With what we start with, any series that absolutely converges actually converges. But it's a telescoping sum. So the series is equal to the sequence of x sub n sub I plus 1 minus x sub n sub 1. So what we're getting here is that if this series is going to converge, then by expanding out what this series is, we should be able to show that the subsequence x sub n sub I actually converges. So that's what this particular thing is going to mean. And that's the general idea behind what's going on in this line as well, is that this subsequence x sub n sub I should be a convergent subsequence of a Cauchy sequence. And guess what? The limit of a subsequence of a Cauchy sequence is if you have a subsequence of a Cauchy sequence that converges, then in fact the entire sequence converges. If you would like to see where this is, take a look at question 7 in the midterm solution document, where I go through and prove that in the thing marked bonus for that, which shows that if you have a subsequence of a Cauchy sequence that converges, then in fact, the entire Cauchy sequence converges. And that ends up getting us to this solution. So that does it for what we need to talk about today. It turns out that normed vector spaces, the notion of a sum, is extremely important because of very much this notion of an infinite dimensional vector space. It helps us turn things into infinite dimensional bases, which we've seen a couple of examples of here in this video lecture today. Starting back from the very beginning, we also talked a bit about equivalent norms on a space. So it's possible for norms to be shared between the space, perhaps even have the same convergent sequences, and perhaps share even more between each other if we can show that any two norms are bounded above and below by the other norm, get multiplied or divided by a constant. But that'll do it for me today. Thank you so much. Have a wonderful day.